So a ball is thrown vertically upwards from the ground. So that suggests a ball vertically upwards from the ground at 40 meters per second. Can you all see that okay? If not, I have excellent viewing seats in the front, lap desks, refreshments. How's it going? Think it through. The acceleration on the object is 10 meters per second downwards. What does gravity do to objects thrown upwards? Speed them up or slow them down? Slow them down. So 10 meters per second tells me it slows it down by 10 meters per second every second. So after 1 second, how fast is the ball going? I asked you a second time. 30 meters per second. So the ball's now right here, but it's not traveling as fast. So I'm going to draw an arrow that's slightly less long and write that it's at 30 meters per second. Why? Because there was an acceleration that acted this way. I'm drawing the acceleration as a different color, downwards. Did the acceleration change after the first second, or is the acceleration the same after the first second? So there'll be another acceleration here during that entire second. What is the velocity of the ball now? Excellent. So after 2 seconds, the ball is traveling half as fast as it was. How many seconds till the ball comes to rest? Class?
4 seconds.
4. Is that too much to ask, or is that all right? Did everybody follow along with how I came up with that conclusion? This will not tell me how far the ball traveled into the air. Unfortunately, it won't. But it definitely tells me that the ball is going to come to rest after 4 seconds. Okay so far? Now I could keep drawing these little pictures. Eventually, I think we all know that the ball will have 0 velocity. And in all of these pictures, there's a arrow pointed downwards. It's the same size all the time, indicating the acceleration is downwards. What I wanted you to see was be able to develop a picture of what's happening. I've developed a picture of what's happening. The problem didn't ask me anything beyond the ball reaching its maximum height. Second, I would like a graphical picture of what's happening. So, you already have kind of a skeleton of this. I want to talk about what it's going to take for you to get 100% on your test. So in drawing a graph, there are several features of the graph that must be very clear. First, a graph is not a graph unless it has labeled axes that include the units. So please make sure you do that. I would encourage you doing it first. Our graphs, unless otherwise stated, start at the origin. Time 0, indicate where the velocity is 0. This is a velocity versus time graph. I was told at time 0 that the object had a velocity of 40 meters per second, and it was positive. Now, I was given the slope of this graph. In the problem, they told me the acceleration was 10 meters per second squared downwards, which is telling me that the slope was negative 10 meters per second squared. That's what the problem told me. I could attempt to draw a line that has a slope of negative 10. The problem with drawing this line is I don't know where to draw it to. I have no points of reference on my graph to help me with what that slope looks like. I could have drawn in an arbitrary scale of seconds, but I knew that we had extra ways of figuring out that this was going to be the 4-second mark. I knew it. 40 meters per second with an acceleration of negative 10 meters per second squared, it's going to give me 4 seconds until it reaches a stop. Use the tools that you have now. Now, I'm going to keep going with this, mostly just to indicate that a graph should have even and well laid out units to explain what we are looking at. Now, we've already handled the idea of slope here. And because of that, we know when the ball comes to rest. But we don't know where. So to discuss where, let's think of the other thing that we talked about yesterday, the area under the curve. We would not have been able to use the area under curve unless we knew the length of this base. So we did have to figure out that time, which we did. But now that we have it, delta x is 1/2 the base times the height. Which by my estimation is 80 meters. The ball rose 80 meters upwards. Okay, so let's consider this. We have conceptualized the problem and drawn a picture. We have been able to flesh out a clear graph that illustrates the exact same thing that was discussed in the problem. The last thing for us to do is to see if there's a way that we could have done this algebraically. And of course there is. So let's talk about the algebraic method of solving this problem. This one's going to be harder for some of you. So let me hit the pause. First, we were told the acceleration was constant. Now here's where we have to tie some pieces together. If the acceleration is constant and the slope of a velocity versus time graph is acceleration, when I put those two facts together, this has to be a straight line. Bless you. Do you understand how I came to that conclusion? Because if you don't, everything from now falls apart. So again, we were told the acceleration was a constant. And we have been learning that the slope of a velocity versus time graph is acceleration. Therefore, the slope had to be constant. It's a straight line. This is a critical piece. Bringing these pieces together tends to be very hard for students. Because if this is a straight line, that means it's y equals mx plus b. You know why I said y equals mx plus b, right? Y equals mx plus b. But don't write that down, because you know I don't believe in y-axis and x-axis. What's on the vertical axis? Velocity. What's on the x-axis? There we go, time. What is the slope of a velocity versus time graph? We are definitely not having that much fun. And of course, my last piece here is at time 0. The y-intercept represents what? Initial velocity, that's right. These are the pieces from yesterday that I want to put in place today. And the truth is, I want to put an F here to indicate it's the final velocity over the interval. Sorry, it'll be back. How about now? Case 1, an algebraic relationship that tells me about the velocity during future points of time. I want to be very clear about this. This is only true when we are told the acceleration is a constant. That's a critical piece. Because that's why it's a straight line. That's why it's y equals mx plus b. Don't forget these little details. These little details are the bread and butter of this class. If you don't assume that you know these details in clarity, you should write them down. Because the next one's going to throw us. This is a trapezoid. Do you remember why it's a trapezoid? It's a trapezoid where one of the bases is 0, but it's still a trapezoid. It's a trapezoid with this being base 1 and this being base 2. And the area of a trapezoid is 1/2 the sum of the bases times the height. But for this trapezoid, Area represents what? What does the area under this curve represent?
Distance.
Not distance. Displacement. That's right, displacement. Got to use our terminology. The 1/2 can stay. It's a constant. Base 1, what does it represent?
Initial velocity.
The initial velocity, that's right. Base 2, what does it represent? Excellent. And the height, what does it represent? Time. An algebraic relationship that will tell us the displacement. In order to tell us this, I need to have these 3 pieces of information. I'm going to jump to another page. Is that okay with you guys for a minute? Yes.
Okay, so I have a question about that. When the velocity reaches 0, is that when it reaches its like peak, when it's highest, or is it when it reaches the ground?
Well, if it reaches the ground, it's not at its highest point, that's for sure. But if it's not going to travel any higher, then that's its highest point.
Okay.
I know it sounds like a ridiculous thing to say, but is the velocity ever going to be positive again? No, because it's going to start coming back down, right? So that would be its highest point, is when its velocity reaches 0.
Okay.
Now, I want to get to took place over 4 seconds. So our new graph, does the ball ever have the same velocity twice?
No.
So, slide here, because I need to really throw something in your face and make sure that there is no misunderstanding about this. We derived these directly from looking at slope and area. You understand that, right? They came from slope and area, but they are all based on one major assumption, that there was a constant acceleration. That assumption is important because we would not have a straight line and we would not have a trapezoid. So other types of motion don't conform to this. This is only when the acceleration is constant. Specifically, it's called uniform accelerated motion. That's the technical term for what we're learning about. Because look, on a multiple choice test, on this chapter, if I give you an acceleration that's changing, none of this works. Okay, none of these equations work. It will still be true that the slope of the velocity graph is acceleration. That's still true. But these equations are based on it being a straight line. That's an important detail, one that gets lost easily with students. I bring it up because if you really look at this, there are 5 different pieces of information presented here. Delta x, vi, v final, a, and t. 5 motion variables associated with uniform accelerated motion. They're repeated in these equations. And if you're very careful, you'll notice that each one of these equations, you got to be kidding me, that each one of these equations has 4 of them in it. Now, that's not accidental, that's consequence. It means, based on my knowledge of algebra, that if you want to solve for any one of these, you must be given 3. Because in any equation, you can only solve for a single unknown. Or you can be given 2, but then you have to have 2 equations. Meaning I can have 2 unknowns here, but I'll need 2 equations to find it. In the problem, the ball was thrown upwards at a velocity of 40 meters per second with an acceleration downwards at 10 meters per second squared and reached a final velocity of 0. 3 pieces of information were given to us at the start of the problem. And we were asked to find the other 2. Can you use these relationships to find the other 2? Well, of course you can. The algebra will work out for us. In fact, I will point out, looking here, I see 4 pieces of information that appear in this relationship. And one of them is the unknown. So if I consider wanting to find the time without drawing any graphs or considering any motion maps, the final velocity was 0, the acceleration was negative 10t plus an initial velocity of 40. How long did it take to reach the top? Well, solve for t. Subtract 40 from both sides, divide by -10, and you get 4 seconds. Not a surprise, right? And now that I have 4 seconds, I can figure out the displacement. How's that so far? Yes, ma'am.
So is the final velocity always going to be 0?
No.
No?
It was in this case because they told us the ball reached the stop.
Okay.
Right? Its highest point was reached when the velocity was 0. They gave us that. Now, they're going to try and trick you. They're going to try and give you problems where maybe they don't appear to give you everything you need. But it is clear to me, and I'm hoping you, that they will have to give you 3 pieces of information for you to use this algebra to do so. Now, I have 2 things I want to demonstrate, and I have only 7 minutes to demonstrate them. So the first thing I want to demonstrate, which requires you guys actually, is I want to ask you to extend what you know so far and see if you can work backwards to what we talked about over a week and a half ago. I want you to create, based on our current problem, a position versus time graph. Please. Is probably the first most important thing I say. This graph is supposed to represent the exact same events as the other graph. Our other graph also takes place over 4 seconds. Time period has to be the same, it's the same events. So, setting these equal to 0. At t equals 0, where's the ball? Only 3 of you? That's too bad. Yes, ma'am? I'm sorry, yes, sir.
At 0.
It's where I am. I threw the ball. Now, I only know one other thing about where the ball is, and that's where it is after 4 seconds. So, where's the ball after 4 seconds? 80 meters. So, I'm going to go to 4 and just put, it's there. That's 80. Now, yeah, I could carefully break this up into, segments, and you should. Now, how do you connect these two? And here's where I think we'll have trouble. Now, I'm going to stop, and I'm going to not put this on. What you're drawing next is important. You have to bring in stuff you already learned, which is the slope of a position versus time graph is velocity. You need that. You can't throw that away. That was last week and the week before. At time 0, what was the velocity? 40. So the slope here should be steep and positive, because the slope here should correspond to 40 meters per second. The slope of a position versus time graph is velocity. So at this instant, this one little point, it's have a slope of 40. At time equals 4 seconds, what's the velocity of the ball?
0.
Say it loud, all of you.
0.
So the slope here should be 0. Look at this graph. This graph should never have the same slope twice. The slope should be constantly changing, starting steep and getting shallow. Think we can draw that? A sketch of the position versus time graph based on what we know about the velocity of the object. Fair enough? All right.